Welcome back. In this video, you will learn about monotonic and bounded sequences. Let's get to it. Alright, so in the previous lesson, we introduced the concept of sequences and how we could determine if they were convergent or divergent by using limits. However, there is another way to determine the convergence of a sequence without using a limit, and it is based on whether a sequence is monotonic and bounded. And we're going to talk about what that means, but I wanted to start off by showing you this theorem. This is what we're going to be working towards by the end of this video. What this specific theorem tells us is that if a sequence, a sub n, is bounded and monotonic, then it will converge. Alright, and so at the end of this video, we're going to circle back to this theorem and try to determine the convergence of some sequences, but first we need to establish what it means for a sequence to be bounded and for a sequence to be monotonic. And we're going to start by looking at what it means for a sequence to be monotonic. Alright, so monotonic sequences are sequences where the terms either increase or decrease with each subsequent term. And so a monotonic sequence that is increasing, the first term will be less than or equal to the second term, which will be less than or equal to the third term, and so on. And sometimes you'll see this called non-decreasing instead of increasing. That's just because there is a possibility that your terms would be equal to each other rather than being less than the next term. However, that's not going to occur a lot, and so it's easier just to say that the terms are increasing rather than non-decreasing. Alright, so in a general sense, what we can say is that for the nth term, a sub n, that is going to be less than or equal to the next term, which will be a sub n plus 1. And so when you want to show that a sequence is increasing, which would make it monotonic, you would want to show that this statement is true, that a sub n, or the nth term of the sequence, would be less than or equal to the n plus 1 term for that sequence. And if you were to divide both sides by a sub n plus 1, another way you could express this is that a sub n divided by a sub n plus 1 would be less than or equal to 1. So that's an alternative way to express that. A term of your sequence divided by the next term of your sequence should be less than or equal to 1. Now, if your sequence is decreasing, that's another way that it could be monotonic. That means that each subsequent term of the sequence is less than the previous one. And so your first term, a sub 1, would be greater than or equal to your second term. Your second term would be greater than or equal to your third term, and that would be greater than or equal to your fourth term, and so on. Now, once again, just like how we call increasing non-decreasing because the terms could be equal, the terms could also be equal here in a decreasing sequence, and so you might see this called non-increasing. And so similar to what we did up here, in general, we would say that a term a sub n would be greater than or equal to the next term a sub n plus 1, right? So for an increasing sequence, a sub n will be less than or equal to the next term. That term is greater than the previous term, so that's why it's increasing. But for a decreasing sequence, the next term after a sub n is going to be less than that previous term. And so each term gets smaller and smaller, which means that the sequence is decreasing. And then similar to what we did up here for an increasing sequence, if we divide both sides by a sub n plus 1, you can see that if a sub n divided by a sub n plus 1 is greater than or equal to 1, then that means that your sequence is decreasing. And so you could use either of these statements to show that a sequence is increasing or decreasing, which would mean that it is monotonic. And we will be looking at examples of using this definition to show that a sequence is monotonic. But first I want to show you visually what a monotonic sequence looks like and what a sequence that is not monotonic looks like as well. Alright, so here we have 3 graphs to take a look at. Each of these graphs is a representation of the terms for the sequence below it, and for each one of these graphs, the horizontal axis represents our values of n, and the vertical axis represents the value of the term at that value of n. And so if you take a look at our first graph here, this represents this sequence, 2 plus negative 1 to the power of n, and if you look at the graph, when n equals 1, our term is 1, when n equals 2, our term will be 3, and then we go back to 1 when n equals 3, and then back to 3 when n equals 4. And so this sequence oscillates between 1 and 3 for its terms, and so there isn't a clear pattern that each subsequent term is either getting larger or getting smaller. It can only go in one direction. In this case, it's going in both directions. We're increasing, then decreasing, then increasing, and then we'd be decreasing again if we were to continue on, and then increasing, and that would continue forever. And so this sequence oscillates between two values, and so it's not monotonic. It is not headed in one direction, whether that be by increasing or decreasing. For our next graph, this is an example of a monotonic sequence that is increasing, and this is the sequence right here, 2n divided by n plus 1. When n is equal to 1, our term is 1. When n equals 2, then we're a little bit higher than 1. When n equals 3, we're even higher above 1. And then at n equals 4, we are even higher. And so each subsequent term is getting greater than the previous term. And so because each term gets greater, this is an increasing sequence, which means it's monotonic. And then for our last graph, this is an example of a monotonic sequence that is decreasing. Each subsequent term is going to be less than the previous term. And so this graph represents the sequence 2n plus 1 divided by n. And so at n equals 1, we have a term of 3. And then at n equals 2, we have 2.5. And then at n equals 3, we're even lower than 2.5. And then at n equals 4, we get even lower. And so each subsequent term is smaller than the previous term, and so this is a decreasing sequence, which means it is monotonic. Alright, so hopefully these graphs help you to visualize what exactly are monotonic sequences, what do they really look like when you graph their terms, but now we're ready to actually look at a sequence and determine if it's monotonic or not. And so here's our first example. We want to know, is the sequence a sub n is equal to 4n divided by n plus 3 monotonic? And so here's how we're going to determine whether this sequence is monotonic or not. We're first going to list out some terms. Typically, I like to write out the first 4 terms. I think that gives us a good look at our sequence. And if we see that the terms are either increasing or decreasing, then we are going to try to prove that by using one of our general statements from earlier for an increasing or decreasing sequence. And I'll show you what that looks like when we get there, but let's start by just writing out the first 4 terms of our sequence. So first we're going to have a sub 1, where n is equal to 1, and so that will be equal to 4 times 1 divided by 1 plus 3, and that will simplify to be 4 divided by 4, and that's equal to 1. Now let's work on a sub 2. So a sub 2 will be equal to 4 times 2 divided by 2 plus 3, and that will simplify to 8/5, and that in decimal form is 1.6. Then a sub 3 is equal to 4 times 3 divided by 3 plus 3, and so that's equal to 12/6, and that is equal to 2. And then for a sub 4, that will be equal to 4 times 4 divided by 4 plus 3, and that is equal to 16 divided by 7. And 16/7 is approximately equal to 2.29. Alright, so now for each subsequent term, we can see that the next value is greater than the previous value. We started at 1, then we have 1.6, which is greater than 1, then we have 2, which is greater than 1.6, and then we have 2.29, which is greater than 2. And so we can see that each term is getting greater, so we know that this sequence is increasing, but we need to prove that. We need to show that it's increasing so that we can conclude that it's monotonic. And so here's how we're going to do that. Remember that we said for an increasing sequence that the nth term, a sub n, will be less than or equal to the next term, a sub n plus 1. Right? The next term will be greater than or equal to the previous term. And that's what we found here for this sequence. And so the way we will prove this is by replacing these terms with what those terms would look like for this sequence. So we know that a sub n will be 4n divided by n plus 3. So we'll have 4n divided by n plus 3, and that's going to be less than or equal to a sub n plus 1. So we're going to use that same sequence, but replace n with n plus 1. So we'll have 4 times n plus 1 divided by n plus 1 plus 3. Right? We just replaced each n in our sequence with n plus 1. Now if we simplify a little bit, we can distribute this 4 through this quantity and then add 3 and 1. So we'll have 4n divided by n plus 3 is less than or equal to 4n plus 4 divided by n plus 4. Alright, and so then what we want to do is simplify this inequality as far as we can up until a point where we can determine if that inequality is true. And so what I'm going to do here is clean up my work, and then we're going to further simplify our inequality by cross-multiplying. In other words, we're going to be multiplying both sides by n plus 4 and multiplying both sides by n plus 3 to cancel out those factors in the denominators. But an easy way to think about that is just to cross-multiply. So 4n times n plus 4 is going to be on this side of the equation. So we have 4n times n plus 4, and that will be less than or equal to n plus 3 times 4n plus 4. So we have n plus 3 times 4n plus 4. All right, so all we did was cross-multiply, and this was the result of doing that. And so now we can simplify. I'm going to continue my work up here. If we distribute 4n through this quantity, we will have 4n squared plus 16n, right? We multiply 4n by n to get 4n squared, and then 4n times 4 to get 16n. And that's still going to be less than or equal to these two factors multiplied together. Now we need to FOIL these terms, so what we're going to do is multiply n by 4n, and that will give us 4n squared. Then we'll multiply n by 4, and that will give us 4n, so we have plus 4n. Then we multiply 3 by 4n, so that's equal to 12n. And then we will multiply 3 by 4, and that will give us 12. So we'll have plus 12. All right, and so now if we simplify, note that we have 4n squared on both sides of the inequality, and so if we subtract 4n squared from both sides, those are going to cancel out, and so now we just have 16n less than or equal to 4n plus 12n. That's actually equal to 16n, so we have 16n and then plus 12. All right, now we have 16n on both sides of the inequality, and so if we subtract 16n from both sides, those will cancel out, and then we'll just be left with 0 is less than or equal to 12. And so now we have our statement all the way simplified, and now all we have to do is determine if this is true. Is 0 less than or equal to 12? Well, the answer is yes, 0 is less than 12, and so this is a true statement, which means that we have proved that a sub n is less than or equal to a sub n plus 1, which means that our sequence is increasing just as we suspected. And so what we can say is that a sub n is monotonic. And if you wanted to, you could say that it is specifically increasing. All right, and so that is the solution to this problem. We were able to prove that this sequence is monotonic by showing that its terms are increasing. All right, so here's our next example. We want to know, is the sequence a sub n is equal to 2/3 to the power of n monotonic? So once again, we're going to go through that same process. We're going to start by writing out some of the terms of our sequence and see if we can determine if it is increasing or decreasing. And then depending on what we find, we will then use a general statement to prove that it's either increasing or decreasing. And so let's write out the first couple terms. A sub 1 will be equal to 2/3 to the first power. That's just equal to 2/3. A sub 2 will be equal to 2/3 squared. So if we square the numerator and the denominator, that's equal to 4/9. Then a sub 3 is going to be equal to 2/3 cubed. And if we cube the numerator and the denominator, that's equal to 8/27. And then let's look at a sub 4 yet. That will be equal to 2/3 to the fourth power. And if we take the numerator and the denominator to the fourth power, we will have 16 divided by 81. Now 2/3 is approximately equal to 0.6 repeating. 4/9 is approximately equal to 0.4 repeating. 8/27 is approximately equal to 0.296 and some more decimals. And 16 divided by 81 is approximately equal to 0.197 and some more decimals. And so now looking at these decimal values, can you determine if our sequence has increasing or decreasing terms? Well, in this case, we started with 0.6 repeating, then we have 0.4 repeating, then we have 0.296, and then 0.197, and so each of those terms is getting smaller. Each subsequent term is less than the previous term. And so we can see that our sequence is decreasing, but now we need to prove it. And so we know that if a sequence is decreasing, that the term a sub n is going to be greater than or equal to the next term, a sub n plus 1. Right? A term is going to be greater than or equal to the next term. We saw that with our terms here. A sub 1 is greater than a sub 2, and a sub 2 is greater than a sub 3. Each subsequent term gets smaller, and so a sub n will be greater than or equal to that next term, a sub n plus 1. Now, a sub n is 2/3 to the power of n, and that will be greater than or equal to a sub n plus 1. So we will replace n in our sequence with n plus 1. So we'll have 2/3 to the power of n plus 1. Okay, so now we want to simplify this inequality and see if we can find a true statement. And the way we can simplify this is we can break up this power here. We can rewrite that to be 2/3 to the power of n times 2/3 to the power of 1. Right, when you have the same base raised to an exponent and you multiply them, you add those exponents. So 2/3 to the power of n times 2/3 to the first power would become 2/3 to the power of n plus 1. We would add those exponents. And so we can reverse that process by breaking this up into those two parts. And we're still going to have 2/3 to the power of n greater than or equal to that. Now on both sides of the equation, we have 2/3 to the power of n, and so what we can do is divide both sides of the equation by 2/3 to the power of n, and that will give us that 1 is greater than or equal to 2/3, right? 2/3 is the same as 2/3 to the first power, and so now we have a statement that we can check to see if it's true. Is 1 greater than or equal to 2 divided by 3? And the answer is yes, this is true. 2/3 is a fraction that is less than 1, and if you weren't quite sure, you could multiply both sides by 3, and you would find that 3 is greater than or equal to 2. That is also a true statement. 3 is greater than 2, and so whichever one of these statements you prefer, both are true, and so what we did here is show that this sequence is monotonic. Specifically, we showed that it's decreasing. And so, if I erase this last term here, we now know that our sequence, a sub n, is monotonic. Specifically, it is decreasing. Okay, and so that is the solution to this example. All right, now before we end our discussion on monotonic sequences and work our way over to bounded sequences, I wanted to show you an alternative way to determine whether your sequence is increasing or decreasing without writing out some of the terms. What you can do is take the derivative of the corresponding function to your sequence. So let's start with this example. Let me show you what I mean. This sequence, a sub n is equal to 4n divided by n plus 3, would have a corresponding function of f of x is equal to 4x divided by x plus 3, right? We just replaced n with x and made it a function. And so if we took the derivative of this function, f prime of x, that's going to require the quotient rule. And so if you don't remember the quotient rule, I'll have it up here on the screen for you to reference. But you take the bottom function, which is x plus 3, and multiply it by the derivative of the top function. And so the derivative of 4x is 4, so we multiply by 4. Then we will subtract the top function, 4x, and multiply it by the derivative of the bottom function. And the derivative of x is 1, and the derivative of 3 is 0, so our derivative is just 1. And then that is divided by the denominator squared. So we have x plus 3 squared. All right, and so if we simplify, this is equal to 4 times x plus 3. So we have 4x plus 12 if we distribute that 4. And then minus 4x divided by x plus 3 squared. Now we have 4x and negative 4x, so those will cancel out, just leaving us with 12 in the numerator. And so if I erase that, then we can see that our derivative is just 12 divided by x plus 3 squared. And now the reason we took that derivative is now we can look at the derivative, and if it is positive for all values of x, then we can determine that our sequence is increasing. If the first derivative is negative for all values of x, then we can determine that it's decreasing. Okay, and so in this case, we have 12 divided by x plus 3 squared. No matter what value of x you plug into this derivative, this is always going to output a positive value, right? Anything plus 3 squared is going to be positive because when you square anything, it becomes positive, and then that's just dividing into 12. And so this is always going to be positive, which means that this sequence is increasing. And that's what we found for this sequence earlier in a previous example. We found that this was monotonic because it was increasing. All right, so since that first derivative is always positive for all values of x, we know that we are increasing, which means that the sequence is monotonic. Now, if we look at our other sequence, this is the other example that we worked on where we found it was decreasing. If we take the derivative of the corresponding function to this sequence, we will find that same result, that it's decreasing. Now the corresponding function here would be f of x is equal to 2 divided by 3, or 2/3 to the power of x, and the derivative of that, f prime of x, will be equal to that exponential function, 2/3 to the power of x, times the natural log of 2/3. Right, the derivative of an exponential function with a base other than e is equal to that exponential function times the natural log of the base. And so we have the natural log of 2/3. Now initially, this looks like it's always going to be positive, right? We have 2 divided by 3 to the power of x. 2/3 to any power of x should always be positive, and then we're multiplying by the natural log of 2/3. However, the natural log of 2/3, if you plug that into your calculator, that's actually equal to approximately negative 0.4054 and some more decimals. And so this constant multiple of the natural log of 2/3 is actually a negative value, and so that means that we're multiplying that negative value by the result of 2/3 to the power of x. And so since this is always going to be positive, and we're multiplying it by a value that is always negative, then this whole derivative is going to be negative for all values of x. And so what that means is that since the first derivative is always negative, that our sequence is decreasing. Okay, and so that's another way to come to that same conclusion, that our sequence is decreasing. Okay? And so maybe you find this method a little bit easier than the previous method for showing that a sequence is either increasing or decreasing. But typically I prefer the other method where we work with the inequality. But I wanted to show you this method as well because it's also valid and you may prefer this over the other method. Okay, but now with that, we have established what monotonic sequences are. And so now let's establish what bounded sequences are. All right, so now we're going to talk about bounded sequences. And so the first thing that you need to know is that if a sequence a sub n is less than or equal to some value m, the sequence is bounded above. And so what this means is that all of the terms of the sequence a sub n are less than or equal to some value. And so visually that looks like this. The terms of our sequence are represented with these red dots, and they are bounded above by that value of m. And what that means is that the terms of the sequence will never reach above that value. They are all beneath or equal to that value of m. And so if you know that the terms of a sequence are not going to be greater than some value m, then you would say that the sequence is bounded above by that value m. The next thing you need to know is if a sequence a sub n is greater than or equal to some value n, then the sequence is bounded below. And so here's what that looks like visually. The red dots, once again, are the terms of our sequence, and they are always greater than or possibly equal to that lower bound of n. They will never get below that value. And so when you see that the terms of a sequence are always going to be greater than some value or possibly equal to it, then you know that it is bounded below by that value n. Now finally, if we put everything together, if a sequence is bounded below by n, but bounded above by m, then we say that the sequence is bounded. So unless a sequence is bounded above and bounded below, it is not bounded entirely. It needs to be bounded both above and below by some value m and another value n. And so what that means, if you look at this visually, the terms of our sequence, these red dots, always lie between or are equal to an upper bound of m and a lower bound of n. They will never go above m and they will never go below n. Now they could be equal to m or n, but they're never going to be greater than m or less than n. Alright, and so if you know that a sequence is going to have terms that will always be less than some value or equal to it, and will also always be greater than or equal to some other value, then you can determine that that sequence is bounded. And so let's take a look at some examples where we determine if a sequence is bounded. Okay, so here's our first example. We want to know, is the sequence a sub n equal to n bounded? And so the first thing you want to do is just determine some of the terms of your sequence. Now this one's pretty easy. The sequence is just n, and so our terms would look like this. A sub 1 is 1, a sub 2 is 2, a sub 3 is 3, and then this would continue on forever. Right, we're just increasing by 1 each time, and so this is a pretty simple sequence. Now if we were to look at a graph of our terms here, let's draw this out. The horizontal axis will be our values of n, and a vertical axis is the value of our terms. when n is equal to 1, the value of our term is 1, so that's our first term. When n equals 2, then a sub n is 2, so that's our next term. When n is equal to 3, then a sub n is equal to 3, and so that would be our next term, and you can start to see a pattern here. We're just going to continue to increase with these terms forever, no matter what value of n we are at. And so if you look at this graph, now I didn't need to draw all of those points there, but if you look at our terms here, is this sequence going to be bounded above by some value? Well, the answer is no. Our terms are going to continue to get greater and greater forever, right? Our terms are 1, 2, 3, 4, 5, and then it would continue on forever, 6, 7, 8, 9, 10, 11, 12, and so on. It's never going to stop at some value. It's just going to keep increasing by a value of 1, and so there's no upper bound m that the terms of our sequence will never go over. They're going to reach every possible value. And so the sequence is not bounded above, but it is bounded below, right? When n equals 1, the term is equal to 1, and we will never have a term less than that value of 1, right? Each subsequent term is just increasing, and so that value of 1 is our lower bound n, and so we would say that this sequence is bounded below by n equals 1. All right, so a sub n is bounded below, so that means it's greater than or equal to the lower bound n, which is 1, and so that means it's bounded below. However, it is not bounded completely because it doesn't have an upper bound. It is not bounded above. And so we cannot say that this sequence is bounded. It's bounded below, but it's not bounded above as well. And so we can conclude that a sub n is not bounded. All right, and if you want to make a note of it, you can say that it's bounded below, but not bounded above. All right, so it might be a good idea to add that to your answer as well. All right, but our final conclusion is that this sequence is not bounded because it doesn't have both a lower bound and an upper bound. It only has a lower bound. Let's look at another example. All right, here's our next example. We want to know, is the sequence a sub n is equal to 1 divided by n bounded? And so let's go through that same process. Let's write out some of the terms of our sequence first. In this case, we'll have a sub 1 is equal to 1 divided by 1. That's equal to 1. A sub 2 is equal to 1/2. That's equal to 0.5. A sub 3 will be equal to 1/3. That's equal to 0.3 repeating. And then let's do one more. A sub 4 will be equal to 1/4, and that's equal to 0.25. All right, and so then if we were to graph out these terms of our sequence, remember that our horizontal axis are the values of n, and our vertical axis are the values of our terms, a sub n. And so I'm just going to graph our first 4 terms here. And so we'll have n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4. Now, when n is equal to 1, the value is equal to 1. That is the value of our term. So that will be our first term. Then when n is equal to 2, we have 0.5. So that will be our next term. Then when n equals 3, we have 0.3 repeating. And so that'll be right about here somewhere. And then when n is equal to 4, it's equal to 0.25, which will be right about here. All right, now by looking at the graph of these terms, can we conclude that this sequence is bounded? Is there some upper bound that these terms will not get greater than, and is there some lower bound that they will never go below or be less than? Well, let's start with the upper bound. We can see from these terms that they are progressively getting smaller towards 0, and so they're never going to be greater than the initial value of the first term, and that is that a sub 1 is equal to 1. So we could say that at that value of 1, the sequence is bounded above. That is the value of m. M will be equal to 1. Our terms are never going to be greater than that value of m. And so our sequence, a sub n, is bounded above by m, and that's equal to 1. So I'm just going to erase m and write 1. But now let's see if it's bounded below. And if you look at the terms on our graph, you can see that they're approaching 0. But if we think about this logically, our sequence is 1 divided by n, and n is only going to be positive integers starting at positive 1, right? And so this sequence is always going to output a positive value. 1 divided by n will never be negative since n starts at positive 1. And so all of our terms we know for a fact are going to be positive. They're going to be greater than 0, and so they will never reach below 0. And so we can say that our lower bound will be 0, and so n is equal to 0. Our terms are never going to go below that lower bound. And so we can say that our sequence is bounded below by 0. All right, so our sequence a sub n, or 1 divided by n, is bounded above by 1 and bounded below by 0, and since it has both an upper bound and a lower bound, the sequence itself is bounded. Okay, and so we can conclude that a sub n is bounded. All right, that is the final solution to this example. All right, and so that's the last example where we focus just on if a sequence is bounded or not, but now we're going to come full circle and revisit that theorem from the beginning. Remember I showed you this theorem that if a sequence a sub n is bounded and monotonic, then it converges. And so now that we know what it means for a sequence to be bounded and to be monotonic, we can test both of those things for a sequence and determine if it converges without ever needing to use a limit. And the reason we would want to do this is that it might be an easier method for determining the convergence of a sequence when the limit method may not be the preferred method, where it might be a little bit more difficult than you would like it to be. And so this might be a nicer way to show that a sequence converges. And so let's take a look at an example where we have a sequence and see if we can determine if it converges based on if it's bounded and monotonic. All right, so here's our first example. Does the sequence a sub n is equal to 1 divided by n cubed converge? And so the way we want to determine this is see if our sequence is both monotonic and bounded. And so let's start by seeing if our sequence is monotonic, and then we'll work on if it's bounded or not. And so we'll start by writing out the first 4 terms or so of our sequence. So we know that a sub 1 will be equal to 1 divided by 1 cubed, and that will be equal to 1 divided by 1, which is equal to 1. A sub 2 will be equal to 1 divided by 2 cubed, and that will be equal to 1/8, and that is equal to 0.125. A sub 3 will be equal to 1 divided by 3 cubed, and that's equal to 1/27th, and that's approximately equal to 0.037 and some more decimals. And then let's do one more. A sub 4 will be equal to 1 divided by 4 cubed, which is equal to 1/64th, and that is equal to 0.015625. All right, now by looking at these terms, can we see if it's increasing or decreasing? Remember, that's what we're looking for if we want to determine if our sequence is monotonic. We want to look to see if our terms are increasing or decreasing. And in this case, it looks like they are decreasing. We started with 1, then we have 0.125, which is less than 1. Then we have 0.037, which is less than 0.125. And then our next term is even smaller. 0.015625 is less than 0.037. And so each subsequent term is decreasing. And so let's try to prove that this sequence is decreasing by using one of our statements. So since we want to prove that it's decreasing, that means that a term a sub n will be greater than or equal to the next term that's going to be smaller, which will be a sub n plus 1. And so let's look at a sub n and a sub n plus 1 for our sequence. A sub n is just 1 divided by n cubed, and that will be greater than or equal to 1 divided by n plus 1 cubed. Right, we just replaced n with n plus 1, so we have 1 divided by n plus 1 cubed. Now if we simplify this expression, let's cross multiply. So we'll multiply n plus 1 cubed by 1 and n cubed by 1, and that will give us n plus 1 cubed greater than or equal to n cubed. And now if we take the cubed root of both sides of this inequality, we will have n plus 1 is greater than or equal to n. And now hopefully you can see that n plus 1 is always going to be greater than or equal to n. If you're adding 1 to n, it's obviously going to be greater than n. But if you're not sure, you can subtract n from both sides of the inequality, and you'll have 1 is greater than or equal to 0. And that is also true. And so since both of these statements are true, we can conclude that this sequence is decreasing, meaning that it is monotonic. And so if I clean up my work here, we proved that a sub n is monotonic. Specifically, we showed that it was decreasing. All right, so that's one half of the problem. In order to determine if this sequence converges, it first needs to be monotonic, and we found that that was true, so that's good. But it doesn't converge until we also prove or also show that it is bounded. And so let's graph these terms here. Let's look and see what happens to our terms visually. Remember that our vertical axis is the value of our terms, and the horizontal axis are the values of n. And so we have 4 to work with here. N equals 1, 2, 3, and 4. And when n is equal to 1, a sub 1 is equal to 1. And so this will be our value of 1 for our terms. So this is a sub 1. Then a sub 2, or when n is equal to 2, that's equal to 0.125. So that's going to be way down here somewhere. And then when n equals 3, it's even smaller than that. So that will look like this. And then n equals 4, or a sub 4, is going to be even smaller. And so you can see from this graph that our sequence is decreasing like we determined, but is there an upper and lower bound for this sequence? Well, similar to one of our previous examples for looking at bounded sequences, 1 divided by n cubed, this sequence is always going to be positive, right? We're only plugging in values of n starting at positive 1 and then increasing towards infinity, and so we're never going to be plugging in any negative values to this sequence. So this sequence is always going to produce a positive term, which means that our terms are always going to be greater than or equal to 0. They're never going to drop below 0. And so we have a lower bound of n, specifically at 0. So our lower bound is n is equal to 0. So we would say that our sequence, a sub n, is bounded below by 0. It is always greater than or equal to that value. But then what about an upper bound? Does our sequence have an upper bound? And the answer is yes. Our first term, a sub 1, which is equal to 1, right? That is the highest value of a term that we will ever have. We already proved that our sequence is decreasing, and so it's never going to come back up above 1. It's going to continue to decrease for all values of n, and so 1 is the highest value that a term will ever be. And so we can say that 1 is the upper bound of our sequence. That is m. The terms of our sequence will never be greater than m, and so they are less than or equal to that value of m, which is 1. So our sequence is less than or equal to 1. And so what we find here is that our sequence is bounded below by 0 and bounded above by 1. And since it is bounded below and above, we can say that it is bounded. And so not only is a sub n monotonic, but a sub n is bounded. And so since we determined that it's monotonic and it's bounded, that means that this sequence does converge. Now, we weren't asked to find the specific value that it converges to, we were just asked, does it converge at all? And so we've answered that question, and so I'll just write down our answer. A sub n converges. And so that is the final answer to this problem. Now, if you were asked to find the specific value that it converges to, then maybe you would need to bring out a limit to show that it does converge to 0. And you can kind of see that from our graph, that our terms are getting closer and closer to 0. So that's what it converges to, but we're not asked to determine what it converges to, just does it converge in general. And so we were able to determine that by showing that a sub n is monotonic and a sub n is bounded. Let's look at one more example for this lesson. All right, so here's our last example. We want to know, does the sequence a sub n is equal to negative 1 to the power of n converge? All right, and so the first thing we want to do is write out some of the terms of our sequence, and we'll use those terms to determine if it's monotonic or not. We'll start with that, and then we'll talk about whether it's bounded. And so negative 1 to the power of n, this is a pretty common sequence that you're probably used to by now. We know that negative 1 to the power of n oscillates between negative 1 and 1. When n is an odd power, it's equal to negative 1, and when n is an even power, it's equal to positive 1. So if we write out the first few terms, we have negative 1, 1, negative 1, 1, and so on. All right, so those are the first 4 terms. We're just oscillating between those two values. And so can you determine, by looking at these values, that this sequence is either increasing or decreasing? Well, since our terms are oscillating between two specific values, it's not increasing or decreasing. Each subsequent term is not greater than the previous term, and so it's not increasing, and each subsequent term is not less than the previous term, and so it's not decreasing. And so, since this sequence is oscillating, we know that it is not monotonic. All right? So we can stop right there. We could just say that we don't know if this sequence converges because it's not monotonic, but let's also see if it's bounded before we make our final conclusion. And so let's graph our terms here. Remember that the horizontal axis is the values of n, and then our terms are the vertical axis. And so we're just going to look at the first 4 terms here. So we have n equals 1, 2, 3, and 4, and the only values that they are going to be are either positive 1 or negative 1. And so if I graph each term, when n is equal to 1, the term is negative 1. When n equals 2, the term is positive 1. When n equals 3, we're back to negative 1. And when n equals 4, we're back to positive 1. And so our sequence here is oscillating between those two values, as we know, but is it bounded above and below by some value? Well, since we know that the terms are either going to be negative 1 or 1, we know that the terms will never be greater than 1, and they're also never going to be less than negative 1. And so this sequence actually is bounded because it's going to be bounded above by m, where m is equal to 1, and it's going to be bounded below by n, where n is equal to negative 1. Now that dot right there is a little bit lower than it should be, and so if I fix that real quick, it should be right at negative 1. It shouldn't be below that line. But anyway, you get the idea that this sequence is bounded above by m, where m is equal to 1, and bounded below by n, where n is equal to negative 1. And so our sequence, a sub n, is less than or equal to 1, but greater than or equal to negative 1. All right, so a sub n is bounded, but it's not monotonic, and so we cannot conclude that it converges. Now be careful here, just because it doesn't meet both requirements doesn't mean that it does diverge. A lot of people will assume that, well, since I couldn't prove that it converges, then it must diverge. And that would be an incorrect way to go about things. Just because we couldn't prove that it converges doesn't necessarily mean that it diverges. All we can say is that this test is inconclusive. We're not able to decide if this converges purely based on if it's monotonic and bounded. All right, but now this specific sequence does diverge because it's oscillating between two values. It's never going to converge to one specific value. So in this case, the sequence does diverge, but there are going to be sequences that are either not monotonic or not bounded that still converge to a value. All right, so don't make the mistake of immediately assuming that it must diverge if it's not one of those two things. All right, so the theorem we're using here is only useful for determining for sure that a sequence converges. It's not useful for determining if it diverges. All right, so you'll see an example of a sequence in my examples video that does not meet the requirements of that theorem, but still converges. And so if you want to see that example, as well as some other examples, feel free to check out my examples video. That will be linked at the end of this video, as well as in the description below. And this is the end of this lesson, so if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.